All right, so let's take a look at section 3.3. Right, so kind of the big idea of this section, we're going to learn how to factor things. Okay? Generally, you've probably done quadratic factoring where you've separated into two sets of parentheses. But we can factor things that have higher powers, and I'm going to show you some tricks for how we can do that. Okay, so again, just to review, I think I said this as I went over the test, but the idea of what is a root or a zero, it has nothing to really do with being a square root or anything like that. All that a root is it's a number you plug in for x, and when you fill it into your function, the answer comes out to 0. Okay, so it's the number, it's the point at which it crosses the x-axis. Right, so again, and you can say it both ways. Okay, this IFF means if and only if. It's from geometry. So you could say if a number is a root, then when you plug it in, you'd get 0 for y. Or you can say if you have a number and plug it in and you get 0 for y, then it's a root. So you could read it as its original statement and its converse. Okay, so we're going to use long division, okay, to find roots of polynomials. You probably did it back in Algebra 2, but it's been a while. So we'll go over that. And let's just look at an example with numbers first. Okay, very simple example. Say I want you to factor the number 12. Okay, factor means write it as a product of two things. Okay, and I'm going to tell you that 3 is a factor. Okay, and I want you to find the other factor. How would you do that? If you want to factor 12, I'm telling you 3 is one factor. What would you do with the 12 and the 3 to get your other factor? Yeah?
Multiple by 3.
Yeah. Right, so the idea is if I tell you 3 is a factor, you know 3 times something is going to give you 12. If you divide both sides by 3, then you can solve for that other factor, which in this case, using division, we'd get 4. Right, so 3 times 4 gives us 12. And notice when we divide 3 into 12, we don't get a remainder. Okay, if you tried to divide a number into 12 and you got a remainder, then that number is not a factor. Like 12 divided by 5. Okay, that would have a remainder when you divide it. That means 5 isn't a factor of 12. Okay, if I divide 6 into 12, no remainder. Okay, that means 6 is a factor. So this idea of getting a remainder of 0, that's an important concept. Right, so basically what I just said. If you take A and divide by B, get a remainder of 0, then you know the number you divided by is a factor of the number on top. And the reason why we're going to do factoring, okay, especially for polynomials, is it makes it very easy to find the roots. Okay, if you've got something, say like this, okay, and we go to factor it, okay, it's a lot easier to find the roots of what's on the right here. Basically, you just have to find the number that would make the first parenthesis 0. Like -2. And that would make the second parenthesis 0, -1. Right? If you can't factor it, it's kind of hard to find those two numbers just by looking at the original. Okay, so that's where the factoring comes in. Right, so we can use the same process we just did with the number 12 with a polynomial. Okay, and we're going to do it using long division. Okay, I'm going to put up the steps for how long division works. It's quite a bit of writing to write out all the steps. It's really, if you're the kind of person that you learn better from an example, you might just want to hold off and watch the example rather than write all the steps. Okay, but if you like steps, I'll kind of put those up. All right, so the first step. If what you're dividing into, okay, the dividend, if it's missing any terms, we got to fill in a 0 for that term. Right? So if you're dividing into something that has its highest power as x to the fourth, you need to have an x to the fourth, x to the third, x to the second, x, and a constant. You need to represent every power from the highest one down. Okay, so if one's missing, fill in a 0. Okay, if you don't, it's going to mess up combining like terms later on. Okay, the second step is to divide the first term of the divisor into the first term of the dividend. Okay, and again, what I think I'll do, let me get all the steps first, and then we'll do a problem, and then we'll kind of go back and look at the steps as we go through it. Okay, after you do step 2, step 3 is to take the answer you just got, that's actually from step 2. Okay, take the answer you just got from step 2. And you're going to multiply that answer by each term in the divisor. And when we write our result, we're going to make sure we line up like terms. Okay, that's what this last part means. All right, so we're going to multiply some things out, and we're going to make sure we line everything up in like terms, in columns. Okay, the next step, after we have everything lined up in columns, we're going to subtract. All right, so just like you learned like in grade school, you do the divide, you multiply, subtract, and then the last thing is bring down. Divide, multiply, subtract, bring down. All right, so the last thing is we're going to bring down the next term, and we're going to repeat that process. Okay, we keep repeating it either until you get a remainder of 0, then you're done, or the degree of your remainder is less than the degree of your divisor. So I think it'll be a lot simpler when we just go through and try an example. All right, so let's try this one. I'm going to take x minus 3, and we're going to divide it into x cubed minus 8x plus 3. Okay, step 1. If we're missing any terms in the dividend, we need to fill them in. Okay, is there any term that I'm missing there? Yeah? Yeah, I'm missing the x squared term. All right, so if I want things to line up, I got to fill in 0 for that. X minus 3. So put x cubed, fill in 0x squared. Okay, am I missing anything else? What do you think, James?
0x.
Yep, we got the x term. Yep. Nope, I'm not missing anything else. All right, so now we can go to step 2. Take the first term of the divisor and divide it into the first term of the dividend. All right, so what would you get if you divide x into x cubed? Or think of it as x cubed divided by x. Yeah, you get x squared. Doesn't matter where you write that. Okay, just put it up top. Right, now we're going to take and multiply the answer we just got, x squared, by each term in the divisor. Okay, so it's going to get, it's almost like a distributive property. And we're going to put the answer under the correct column. So let's start with x squared times x. Derek, what's x squared times x?
X cubed.
X cubed. And what's x squared times negative 3?
3x squared. Or negative 3.
Negative 3x squared. Okay, this is why I put the 0x squared in. If I didn't, I wouldn't have had a spot to put that. Okay, so I got my x squareds lined up. Okay, the next step, you're going to subtract the columns in step 3. Okay, what I always do so I don't forget, put it in parentheses, because you're subtracting both of these. Okay, start with x cubed minus x cubed. Yeah, that's gone. Okay, and then the next one, 0x squared minus 3x squared. Positive 3x squared. Okay, that's a mistake people will make. They'll forget that it's minus 3x squared. Okay, that's step 4. And now step 5, bring down the next term, minus 8x, and repeat. And that's it. So if you understood what we did there, it's basically what we're going to do again. I'm going to divide x into 3x squared. Okay. Cameron, what would you get if you take 3x squared and divide by x?
3x.
Yeah, you'd get positive 3x. All right, now multiply the answer we just got to each term. Make sure you put it in the appropriate column. Okay, Brian, what's 3x times x?
3x squared.
Yep. Okay, you should always get that term back because it's going to cancel out right now. Okay, so that should always happen. And then, Brian, what's 3x times negative 3?
It's negative 9x.
Good, negative 9x. Step 4 is to subtract. But what should I put in so I remember to subtract the whole thing? Yep. And now we subtract. 3x squared minus 3x squared. That's gone. What's negative 8x minus 9x? Just x. All right. So now the first time we did it, we brought it from a degree 3 down to a degree 2. Right? Then we did it again. We brought it from degree 2 down to a degree 1. We have to keep going until the degree of our remainder is less than the degree of the divisor. Right now, they're the same. X is degree 1, and then that x is also degree 1. Okay, so do it one more time. And this will be it. Leon, what's x divided into x?
Say it.
What do you get when you divide x into x?
I don't really know. I don't know.
Sure. Aiden?
You get 1.
You get 1. Yeah. So when you divide two things that are the same, okay, we get 1. And now what do I do with this 1? Dave?
Multiply it by x.
Yep, multiply 1 times x, which is x, and what else?
Multiply 1 by negative
1 times negative 3, which gives me
3.
negative 3. Okay, and Ashley, what's my last step going to be here? Subtract. Okay, so subtract it. X minus x, that's gone. And Ashley, what's 3 minus 3? 6. And that's my remainder. All right, so there's a couple ways you can write your final answer. You can write it as, right, you have a quotient, which is x squared plus 3x plus 1. And the remainder is 6. Okay, that's one way you can write it. Okay, the other way you can write your answer is kind of how you do it when you use numbers. Let's say I took 12 divided by 5. Let's not use 5. Let's use 13 divided by 5. Okay, if I were to do this one, the quotient would be 2, and the remainder 3. Okay, if I did that one. Any question on that? Okay, one way you can write this answer is 2 plus. Anybody know how I can write the remainder? We write that part as a fraction. As what? 3 over 5. You can write it that way. Right, let me show you that. I'll remember that works. Okay, there's 13 divided by 5. 2.6. Right. Here's 3 divided by 5 plus 2. 2.6. Okay, so another way you can write your answer is take your quotient. Actually, you know what? Let me write it this way. quotient plus your remainder over your divisor. Okay, that's another way you could write an answer. Just like you did back in basic arithmetic. Remainder over divisor. Right, so if I wanted, I could write this problem as x squared plus 3x plus 1 plus 6 divided by x minus 3. Okay, for now, I think I'm just going to leave it as quotient and remainder. Okay, any question on that? Okay, how many people have done that before? That long division? Kind of remember? Yeah, back in Algebra 2. Probably not in geometry. All right, let's try this one. What I did here is it was missing a couple terms. I already filled them in for you. 0x squared and 0x. All right, so John, I'm going to start off. What do I get when I divide 2x squared into 2x to the fourth?
X squared.
Perfect, x squared. Okay, multiply it back out and line everything up. 2x to the fourth, x cubed, plus x squared. And subtract all of that. Okay, Dominic, 2x to the fourth minus 2x to the fourth.
Nothing.
Yeah, it's gone. Negative x cubed minus x cubed.
Negative 2x cubed.
Good, negative 2x cubed. And 0x squared minus x squared.
Negative x squared.
Negative x squared. And bring down my next term, which in this case is just a 0. Okay, now the degree, notice it's one smaller. It's down to a degree 3. That's a degree 2. Okay, we got to keep going. Okay, till this number is smaller than that number. All right, so I'll do the next one. We're going to divide 2x squared into negative 2x cubed. Okay, that's going to leave me with negative x. Okay, the way you can double check if you're right, multiply it back out, and you better get that back again. All right, so negative x times positive 2x squared, that is negative 2x cubed. Okay, minus x squared, and minus x. Okay, now watch what's going to happen here. We got negative 2x cubed minus 2x cubed. That's gone. What's going to happen here? Negative x squared minus negative x squared. Yeah, so sometimes when you do long division, two things cancel at the same time. So that just made it one step shorter. Okay, we're not going to have any x squareds left. And then we just have x. So at this point, I'm done. Okay, the degree of my remainder, okay, is a 1. The degree of my divisor is a 2. I can't divide something that's squared into something that's to the first power. Okay, so I bring down my remainder, and that's it. Or I bring down the last number. Okay, so my quotient is x squared minus x, and my remainder, x minus 2. Okay, so remainders don't always have to be numeric. Okay, question on that? All right. All right, so I kind of showed you guys this a little bit. But the idea is if you divide two numbers, okay, when you divide them, you get the quotient and you get a remainder. And you can add that remainder on to the end. Let's look at an example with numbers. Okay, let's say I did, let's say 12. Let's use that example we had. Okay, so 12 divided by 4 equals 3. In this case, actually, there wouldn't be a remainder. So you know what? Let's make it something with a remainder. 14 divided by, yeah, we could do 14 divided by 6. Okay, so we get 2, and the remainder 2. So if you're going to write this out, the way you could write it is h of x, okay, that's what I divided by, 6 times my quotient, which is 2, plus my remainder, which is also 2. Right? And if that comes back out to the numerator, then I did it correctly. 6 times 2 is 12, plus 2 gives me 14. So that is correct. All right, so in this problem, think of f of x is 14, h of x is 6, quotient is 2, and remainder 2. Think of it like that. Any question on that idea? So I like to think of it as denominator times quotient plus remainder gives you your numerator. Okay, so remember, we already wrote this down. Keep dividing until the remainder, the degree of the remainder is less than the degree of the divisor, or you might get a remainder of 0, and then you're definitely done. Okay, so if we divide something by a linear polynomial, okay, and we got to keep going till the degree is less than linear. Okay, well, the only thing less than linear is just a number, okay, a constant. So anytime you divide by something that's linear, like x minus 2, x plus 6, right, x minus 5, that's linear. Your remainder will always be a constant. And sometimes all we want to know is the remainder. Okay, we don't actually care what the quotient is. We just want to know if you divided this by that, what would the remainder be? Okay, and I'm going to show you a shortcut how you can get the remainder, okay, without going through all the division. All right, so let's say we take some function, f of x, and divide it by something linear. Okay, like c would be a number, like x minus 4. Well, using basically the formula we have up above, okay, the numerator equals the denominator, which in this case is x minus c, times the quotient, which we don't know what the quotient is, okay, it could be anything, plus the remainder. But remember, that remainder is going to be a constant, okay, as long as you're dividing by something linear. If you start dividing by something like x squared, then your remainder might not be a constant. It could have a letter in it. Okay? Just pretend like we're dividing by something linear. Okay, any question on that? So numerator equals your denominator times the quotient plus the remainder. Now I want to look what happens if we let x equal c. Right? So it's almost like we're actually plugging in a c right here. Okay, watch what happens. You get f of c equals, and I'm changing all my x's to c's, c minus c times q of c plus r. Well, what happens when you do c minus c? You get 0. And what's 0 times anything? So what are you left with? All you're left with is r, which is your what? Remainder. All right. So if you're dividing by something linear, okay, and all you want to know is the remainder, all you really have to do is take that number, okay, whatever comes after the minus sign, plug it into your function. The quotient will automatically just cancel out. You won't even have to worry about it. And when you plug it in, all that you're going to get is your remainder. And that's called the remainder theorem. Okay, it only works if you divide by something like this. If you divide by x squared plus 7, yeah, it doesn't work. You've got to divide by x minus a number. Okay, so point here, you can get the remainder if you divide by something simple without actually doing division. You could always use division to check it, but this makes it very easy. All right, so we're going to take a couple different functions, divide them into f of x, and see what we would get for a remainder. Notice here, all I want is the remainder. I don't want the quotient. So let's start with f of x divided by h of x. First thing I got to do is look, am I dividing by something that's of the form x minus a number? Brian?
We're dividing by x minus 3.
Yeah. So is that what I'm looking for? Yeah. Okay, we are dividing by x minus a number. Right, so we've got x cubed minus 2x squared plus x minus 5. It's all divided by x minus 3. Perfect. Okay, so all I really need to do here is take c, plug it into function f, and I'll get the remainder. Okay, what is c in this case? 3. Okay, be very careful with that. C is the number after the minus sign. Okay, C is what comes after the minus sign. So all you need to do is find that. Plug 3 into function f, and that's your remainder. Okay, quotient, it's just going to cancel out. It's part of the theorem. We already went through the reason why. So we get 3 cubed minus 2 times 3 squared plus 3 minus 5. Okay, Aiden, what's 3 cubed?
Oh, 3 is 92, 27.
Yep, 27. All right. Minus, okay, 3 squared is 9 times 2 is 18 plus 3 minus 5. Okay, if we want, let's just use our calculator. We got 27 minus 18 plus 3 minus 5. There's your remainder. All right, so if you were to do all this workout using what I just showed you, that's what you'd get for a remainder. If you want the quotient, at least for today, there's no fast way to do this. I will show you a fast way to do this tomorrow to get the quotient. Okay, let's try the next one. Okay, the remainder for f of x divided by g of x. Okay, so my numerator is still x cubed minus 2x squared plus x minus 5. But what's going to go in the bottom? G of x is x plus 1. You could write it as x plus 1, but I wouldn't. How should we rewrite that? X minus negative 1. Okay, you've got to have it in the form x minus c. And now, what is my c in this case? Negative 1. Good. Okay, so take negative 1, plug it into function f, and that will tell you your remainder. All right, so we got negative 1 cubed minus 2 negative 1 squared minus 1 minus 5. Okay, so negative 1 cubed is negative 1. Negative 1 squared is positive 1 times negative 2. It's negative 2 minus 1 minus 5. Okay, what's negative 2, negative 1 minus 2? We got negative 3. 3 minus 1,
4, negative 4.
and then minus 5 more,
Negative 9.
negative 9. Good. So that's your remainder. Okay, questions on how to use the remainder theorem? Don't do the division if you don't have to. Okay, use the theorem.
Wait, I just have a question. So g of x is equal to x minus negative 1.
In this case, it was, yes. Yep. The reason I rewrote it as minus is because I want to make it look like x minus a number. Okay, any other questions on that? All right. All right, so if we divide f of x by x minus c, okay, we could write it this way. Okay, we've already talked about using the remainder theorem. Okay, but now I want to look at what happens if it's a root. Okay, suppose that c is actually a root of f. Okay, that means when you plug it in, you'd get 0. All right, so taking that above equation, okay, if c is actually a root, I'd plug in c, okay, I would get 0. And that means this whole part would just disappear. So basically what this tells us is that if you plug in 0, it gives you a way to, if you plug in something and get 0, it tells you it's a factor. It gives you a way to factor something, okay? Because there's no remainder. So it takes a function and it allows you to rewrite it as something times something, all right? But the whole key is you have to plug in your number and get 0 as a remainder. Right, so again, what the factor theorem tells us is if you divide by x minus c, and you plug c in and you get 0 as a remainder, then it's a factor. Right, so that's where this remainder theorem is going to come in handy. We'll plug in a number, we'll check it, see if the answer comes out to 0. If it does, then that tells us whatever we're dividing by goes in evenly. It is a factor. Right, so the factor theorem it's really kind of like the remainder theorem, except it's a special case when the remainder comes out 0, and it tells you something special. Okay, if the remainder doesn't come out 0, you do not have a factor. It doesn't go in evenly. Right, so rather than have you guys factor this one, okay, for the first one, I just want you to show me that x plus 2 is a factor of x cubed plus 5x squared plus 5x minus 2. Okay, so how do I show that this is a factor? Or what does that mean again? If I were to divide this in and it's a factor, what would happen? I would get a remainder of 0. So really all I have to do is show that if I divide this into this, I get remainder 0. Okay, now there's two ways to do it. You can go back to the way I showed you at the beginning of class. Or just use the remainder theorem. Okay, if I use the remainder theorem, what number would I be plugging in? Right. You're taking x cubed plus 5x squared plus 5x minus 2. And we're going to divide that whole thing by x minus 2. Prove to me that you get a remainder of 0 when you do that. And that will answer this question. All right. So let's fill in negative 2 for x, okay, in the numerator. So negative 2 cubed plus 5 times negative 2 squared plus 5 times negative 2 minus 2. Okay, negative 2 cubed, yeah, negative 8. How about the next part? Plus 20. And negative 10. And on the end? Minus 2. All right, negative 8 plus 20. It's going to give me 12. 12 minus 10 is 2. And 2 minus 2 is 0. So I just proved that if I divide this polynomial by x plus 2, the remainder will be 0. Which means that what I just divided by is a factor. Any question on how I proved that that's a factor? And that's it. That's all you have to do to prove that. All right, so I'm going to just kind of remind people of what those statements about roots and zeros mean. They're the same thing. Okay, all of these statements that I'm about to put mean exactly the same thing. Okay, in this statement, I'm saying C is a number that if you plug it in to the equation, you'll get 0 for y. Okay? That's the same thing as saying C is a 0 of the function. Or you could say C is a root of the function. Or you could say x minus C is a factor. Okay? And that's the important one. Okay, so if I said to you 5 is a number that you can plug into the function and get 0, that means 5 is a root. Or x minus 5 is one of the factors of that polynomial. Okay, so if something is a root, x minus that root is a factor. Okay, and we could also think about it graphically. Okay, if it's a root, it's where it crosses the x-axis. Okay, that's an x-intercept. Okay, any questions on any of those statements? So let's try to use that idea to answer this question. Okay, rather than me give you a polynomial, I want you to come up with a polynomial where these three numbers are roots, or zeros, or x-intercepts. Okay, and I want it to be a degree 3 polynomial. In fact, it would be impossible to make it any smaller degree. You couldn't do this with a parabola, because parabola can only cross the x-axis twice at most. I want you to cross the x-axis 3 times. All right, so let's start with negative 2. If you know that negative 2 is a root of that function, what else does that tell you? If negative 2 is a root, think about what would be a factor. Yeah?
It would be
Plus 2. Right. Okay. If negative 2 is a root, then x plus 2 is a factor. Does everyone see why it's plus? Because it would be x minus negative 2. Okay. What would be another factor? If 1 is a root, what else would be a factor?
X minus 1.
X minus 1 is a factor. And if 3 is a root, what do we know is a factor? X minus 3. Okay, let's graph that. Okay, if we graph it, I guarantee you it's going to cross the x-axis in those 3 spots. Right? You could foil it out or just leave it like this. It'll be easier. Okay, x minus 1 and x minus 3. Okay, do zoom 6. And there's our graph we just made. You can see it. It crosses the x-axis exactly where we wanted. -2, +1, +3. Okay, so when I'm making a test question, if I want to make a graph and force it to go through certain routes, that's how I can do it. And then I could take all this and FOIL it out, so it would look like x cubed, minus 2x squared plus 6x minus 7, something like that. Okay, and then have you work backwards to find these routes. Okay, so any question on how to make a polynomial go through certain routes? Okay, what do you think would happen if I did, let's make it x plus 2, x plus 2, x minus 3. What's going to happen now? All right, it might do some, it might shift a little bit. What about in terms of the roots? What do you think my roots will be? I'm not gonna, yeah, it's just going to come down. It's just going to touch the -2. So -2 will be a root. And what's my other root? 3. So this one's only going to cross the x-axis twice. It's going to come down, touch it, go away from it, and come back. Right? This is called a repeated root. Okay, anytime you have a root or a curve that kind of comes up, touches something, and goes back away from it, it's probably because you have the same root repeated. Okay? You could even repeat it 3 times. All right? And then if I did that, how many times would it cross the x-axis now? Just once. It's just going to look like a curve going straight up. It's never going to turn back. All cubics. Okay, those are all cubic equations. Just different numbers of roots. Okay, any questions on that? All right. This one, I want you to try to find the zeros. Okay, find the roots. And I'm giving you a hint on how to try it. Okay, to factor by grouping. Okay, so factor by grouping is when you take something the first 2 terms have in common, factor that out. Something the second 2 terms have in common, and then factor that out. All right, so take a second, see if you can try that. Okay, factor what you can out of the first 2 and the last 2, and then we'll try to look at it together. Cameron, what did you factor out from first 2 terms? Yep, you can factor out an x squared. Okay, and what does that leave you with in parentheses?
X plus 2.
We get an x plus 2. Now, with factor by grouping, my hope is I see x plus 2 again later on. Okay, that's what needs to happen. Okay, Nick, what were you able to factor out from the second 2 terms?
-4.
Yeah, factor out a -4. And if you do that, what does that leave you with? It does. It's -4x minus 8. Okay, now I'm going to look at each one of these terms. Okay, and Leon, what do each one of these now have in common?
X plus 2.
Yeah, they each have an x plus 2, so now I'm going to factor that out. Okay, and Derek, if I factor x plus 2 out of the first term, what does that leave me with?
X squared,
Just x squared. And what if I factor it out of the second term?
-4.
Just a -4. Okay, now once we've factored it, it should make finding the roots pretty straightforward. Sorry, x squared minus 4. Okay, let's start with my first factor. John, what would make that first factor equal to 0?
-2.
Yep, -2. -2. Okay, so that's one answer. And now we're going to set that second factor equal to 0. Right? All right, how did you get 2?
Because x squared minus 4 is 0, and and 2 squared is 4, so 4 minus 4 would be 0.
Okay, I do agree with you. That's one answer. But we lost one answer here. Okay, and I'm just going to add 4 to each side, and maybe someone will see the second answer now.
This could also be -2.
-2. Yep. So we get, from this one, okay, take the square root of each side. You get x equals positive or -2. So what are my roots really here?
Positive and -2.
Just positive and -2. So this is a cubic. That was the highest exponent. What would happen if I graphed it?
It would just touch -2.
Yes. Because you have a repeated root, -2, it's going to just go, it's going to touch -2 and go away from it. It's never going to cross. And then at +2, it's going to go right through it. All right, so finding these roots, especially a repeated root, gives you an idea of what it'll look like. All right, and this will be our last one. Okay, this one, if you tried factor by grouping, I don't think it's going to work very well. Okay, if you factor an x squared out of the first 2 terms, you're left with a 2x minus 4. And, well, you could factor out a, let's see, with that, actually that might,
Factor out 2x.
2x squared and 1.
yeah, it might, actually that might work by factor by grouping. We're not going to do it that way, but you probably could. If you factored out a 2x squared. That's a good point. Let's just graph it, okay, and try doing it on the calculator. All right, so we got 2x cubed. Minus 4x squared plus x minus 2. Right, so if we can do factor by grouping, I would expect the answer to come out nice. Probably not a decimal here. And it looks like it's pretty close to 2. Did anybody calculate the root?
Yeah.
And what does it come out to?
2.
It does come out to 2. So find the zeros. X equals 2. So what do you think that would mean this factors as? If 2 is the only root in the problem. Yep, x minus 2. What about the other factors? X minus 2, and the third factor? X minus 2, right? It would have to be the same root 3 times. And you could prove that by doing it out. Or you could kind of get an idea by graphing this. Graph x minus 2 times x minus 2 times x minus 2. See if it looks the same. Okay, so in this case, it clearly doesn't. So it does have the same root, okay, but it doesn't quite work. So it was a good guess to think what it might factor as, but it wasn't quite that simple. But same root, so I'm glad you at least saw that. Okay. All right, I guess the only way we could factor, what did we say to factor out with grouping? Let's see what happens. Yeah, you'd be left with x minus 2 plus another x minus 2, and then factor that out. So you'd be left with 2x squared plus 1. That's what it factors as. X minus 2 times 2x squared plus 1. Any questions on that? So, okay, for tonight, the homework's on 171. Okay, I'd like you to try 1, 2, 4 through 6. Yeah, I skipped a couple, 9, 11, 13, 15, 17, okay, 19 to 21, and then 25, 27, and 32. Okay, we'll take a look at that tomorrow. Also, don't forget, tomorrow is picture day, so right at the beginning of class, we'll go down, we'll do our pictures, and then we'll head back up.